Let's solve some of these problems. True or false, all of these reactions...
No, true or false?
all of these reactions can use things that we've covered only in Unit 5. You guys look confused by the reaction, but you see it, right?
Did Unit 5 start?
Can we? Do we need to? That's what I'm asking. Are all of these things strictly from Unit 5? Which Unit 5 started with that worksheet on alpha hydrogens. So the only thing that we've seen so far is alpha carbon substitution. Can I borrow this just to put these up? Oh, I screwed up. Yeah, I screwed up bad. Whoops. Down here, I put heat. Heat alone is not going to do anything in that reaction. We need acid and heat. And a reminder that heat is delta. Delta is heat. So, true or false? All of the reactions that you need for these problems were from Unit 5 alpha carbon substitutions. Yeah. For which one? Well said. In fact, there was nothing that we learned in Unit 5 that talked about oxidation. The only thing that makes this work is PCC. And we learned that in Unit 3, right? Somebody asked me today if the final is going to be 50-50 between pre-midterm, post-midterm. And it's usually between 50-50 pre- and post-midterm material and like 2/3 post-midterm, 1/3 pre-midterm. But to be honest, there's so many things that came from pre-midterm that are relevant post-midterm. So it often is more like 50-50. Okay, what else can I do here? Andy, you want to give me a reagent that takes me from acetaldehyde to chloroacetaldehyde?
That's the one I don't have. The one.
I'm sorry. Sorry to call you out like that. Anybody else? From acetaldehyde to chloroacetaldehyde. Sure. Cl2 is necessary. HCl can be written a different way. Any acid works here. HCl will produce H3O+ in water. So HCl is great. But I hope you don't think HCl is needed to get the Cl on. The chlorine at the alpha position comes from elemental chlorine. The acid is just acting as a catalyst to make the alpha carbon a nucleophile.
When did we learn
At the top of our reaction diagrams for alpha carbon substitution, acid and halogen.
Oh, I think what was throwing. Oh, because that one.
We did bromine. Yeah, it substitutes an alpha hydrogen for a halogen. And it does it once. It stops at doing it once. Acidic conditions will monohalogenate. How does that differ from basic conditions? Acidic conditions do monohalogenation. And that top left reaction diagram from our last worksheet didn't do a great job highlighting that because it also went to the more substituted position. So we showed it again with the ketone that only had one alpha hydrogen position. Acidic conditions are monohalogenators. What happens in basic conditions?
Same thing with sodium hydroxide. Both the bulkier base, you get di-2 substitution.
Yes and no. So if I have different degrees of substitution, a small base like this goes to the more substituted alpha carbon. If that's a tertiary alpha carbon, it can only monohalogenate because there's only one substitution it can do. If that's a secondary alpha position, it can only dihalogenate. But if it's a methyl group, if the methyl group is the only alpha position with alpha hydrogens, then it just does a runaway reaction in substituting. So it doesn't just halogenate 3 times, but it then substitutes that tri-halo methyl group. And in basic conditions, leaves it deprotonated. That is a named reaction. Sorry, by name, I don't mean a dead guy's name, but the name of the chemical that it produces. Do you remember the name of that reaction? The haloform reaction. You said it, the haloform. Yeah. All right, let's see if we can recognize again the unique conditions required for the haloform reaction. It needs a methyl group. Otherwise, it won't be able to kick off the alpha carbon. It needs a methyl group that it can halogenate 3 times before it substitutes it. And it needs that methyl group to be the only alpha hydrogen position, because a methyl group is the least substituted it can get. So if there is another alpha position on the other side, that other side is going to be halogenated. Okay. What about to the right? Keep in mind this modification. Heat was not enough. I don't know why I said that. That was a bad mistake on my part. What reagents do I need going down? What do I need going right? What do I get from acid and heat in the middle? Or to, on the bottom, to the right. Elimination? I won't do elimination. What I need is to remove an alpha hydrogen and substitute that alpha hydrogen with an alkyl group. So really I need to do alkylation. To alkylate these, I'm going to need a base that can turn the most acidic position into a nucleophile. So we can start by saying first a base. Can I add NaOH? Esters with NaOH are saponified, and they leave you with carboxylates. So no, No sodium hydroxide. What can I use as my base here? Terbutoxide is not great because then it can trans-esterify. And it would leave me with a tert-butyl ester instead of a methyl ester. No, it's not the new one that we learned, which we're going to talk more about today.
We need it to match the side chain.
We need it to match the ester linkage. Yep. So in this case, something like sodium methoxide would be great. You guys ever worked with an alkoxide in lab? You haven't. That was a rhetorical question. You haven't. And I find that this is kind of limiting in our lab experience. We talk about these types of reagents a lot in lecture courses, nucleophilic oxygens, but you never use them at all in our lab courses. So it's something I'd love to modify about our labs. This is actually a good base for this hydrogen. This hydrogen has a pKa around 16, and the conjugate acid, methanol, has a pKa around 16. So this is 1,000 times more acidic. What can I introduce next?
Carbon chain you want to add with the leaving group.
Good. So a good way of figuring that out is to count your carbons. I'm going to look at the product. This is my nucleophilic carbon, carbon 2. I want carbon 2 to attack carbon 3. So I want a leaving group on carbon 3. And then 4. 4's got a methyl group, and then 5. So I'm looking for this 3, 4, 5 with a leaving group on 4. 3, 4, 5. And a leaving group on 4. Is that an all right leaving group? Chlorine works. Bromine works. Tosylate works. What about if I did an alcohol, OH? No, alcohol is not a good leaving group. What if I put an an ether, OMe? Ether is not a good leaving group. So halogens or pseudohalogens work great here. So what is different about the synthesis to the right? Sure, I just need an alkene in my structure. First, a base that matches my ester linkage, which in this case is a methyl ester, and then a carbon chain that matches what I want in the product. In this case, I'm doing an allylic leaving group. Do you guys remember the term allylic? Adjacent to an alkene. Vinylic is attached to the alkene. Allylic is off of the alkene. 3, 4, 5. Just helping me make sure that I've got my carbon chains correct. All right, down below, if I had just put heat, nothing really happens. But by putting acid and heat, especially aqueous acid and heat, I first hydrolyze, so I don't isolate this product, but I get malonic acid. And what does the malonic acid turn into after the heat? Can you name it? You have to name it on the final. Draw it out, and then write its IUPAC name. It's because I care about you. I care about you crying at home when you're studying. Sorry, that did not land well, clearly.
name this?
Nope. Name what it turns into. Name the product of the...
I thought
Do
you
you-
were naming the one in red.
No.
Oh.
No. Sorry, I'm not that mean. Mm-hmm. Oh, no, not. This is the wrong root.
1, 2, 3.
No.
Wrong root? Is that
Wait,
what it
did
is for?
am
Wait. No, I'm terrible at naming.
I think you missed a carbon. When you counted, I think you missed a carbon.
Did I miss a I don't even know what happened.
Who wants to help Ella figure out what happens?
I don't even know. Do you know? Okay, as long as I'm not the only one.
Earlier on your sheet, do you see anything that resembles it? Okay.
I'm a bit behind.
It's okay.
I'm one lecture behind.
Okay. How about this? Can you name the functional group that I have highlighted in that red box? What could you best use to describe that functionality?
Thought we were naming the product.
Yeah, we are naming the product. They don't lead to the same product.
Oh, they don't? That makes sense.
They've got different carbon chains, yeah.
Makes sense.
You don't know what it does? What can you use to describe that functional group? Do you remember those names I gave you on the first day of this unit? Like alpha beta unsaturated, beta carbonyl carbonyl. That's a big umbrella, beta carbonyl carbonyl. This is not a beta keto ester. It's not a beta ester ester. This is a beta carbonyl acid. And every beta carbonyl acid, regardless of what the other carbonyl is, can go through decarboxylation. Remember that this heat step actually forces the structure into this high energy conformation, where it then undergoes intramolecular decomposition. This beta carbonyl takes the acid's proton. The OH bond forms a CO double bond. And then the carbonyl to alpha carbon bond shifts over to support the carbonyl carbon that's losing electrons. So what we get is the enol version of a carboxylic acid in this case, plus CO2. And as we know, enols tautomerize. So when this enol forms, it tautomerizes back into a carboxylic acid. What you guys have in your on your worksheet we showed a beta keto ester being hydrolyzed into a beta keto acid instead of a beta acid acid. This is what we have on our worksheet earlier. And then we said that the heat drives the decarboxylation. What's the difference between the example we already considered in decarboxylation versus the example we're considering now in decarboxylation? The final product. What differences do they have? Ketone is what I demonstrated. Carboxylic acid is what you ended up with. Why does this have to be a ketone? If I pulled out this methyl group and I left it as a hydrogen, now it's an aldehyde, and it's still an aldehyde. Decarboxylation doesn't need to leave a ketone. If I had left it in, but I had a carboxylic acid instead of a methyl group, now I'm left with a carboxylic acid instead of a ketone. The key feature of this decarboxylation is that you're left with a carbonyl on one side with the alpha carbon intact. And you cleave off one of the carbons, one of the carbonyls. You cleave off the carboxylic acid's carbonyl. Milena?
So basically, is it always going to be like beta-carbonyl ester or something? Like, do you need the ester on the side? Or?
You would need an ester, but the ester can't go through this decarboxylation because it doesn't have a hydrogen. Decarboxylation requires that esters become hydrolyzed first. So it doesn't need an ester. Any way that you can get to a carboxylic acid, that's what's needed. A beta carbonyl, although in this case it happened to be a beta keto acid. In this case it happened to be a beta acid acid. But any beta carbonyl acid decarboxylates.
And you did that by adding heat and H3O+?
Right, so the H3O+ serves what role? Hydrolysis. The heat drives the decarboxylation.
Okay.
Mm-hmm.
So I think I'm getting confused that we have the esters, but then the esters have methyl groups on them.
Sure.
Where did the methyl groups go?
Well, in hydrolysis, alcohols are a byproduct. Esters react with aqueous water to form alcohols and carboxylic acids. So the alcohol is not what I'm interested in. If it helps, I can show you that we have two equivalences of methanol here as a byproduct of the hydrolysis. What about up here? What is my byproduct? One equivalence of ethanol. I hydrolyzed my ester. I have a byproduct of alcohol. Great question. And guess what? You know the hydrolysis mechanism. Protonate, acyl addition, deprotonate, protonate, elimination, deprotonate. Simple, easy. Did I tell you guys I'm modifying what I'm going to do for the Unit 4 Part B? I'm going to add another mechanism. Took you guys way too short of time to solve that. So.
Wait, what?
Also, I've told you guys that my mechanisms are based on the number of steps, right? But on the Unit 4 Part B, I had some of you show me acetal formation or hydrolysis, and others show me esterification or ester hydrolysis. But acetals are a 7-step mechanism and esters are a 6-step mechanism. So I can't have different people solving different number of steps. That makes it really hard for me to grade it consistently. So what I'm going to try to do is add to the 7-step mechanism a 3-step mechanism that also has to be done. Like 2 reaction mechanisms you have to show me on the Part B unit test. And for the 6-step mechanism, I'll add a 4-step mechanism that has to be done.
So we have to take that unit test again?
No, sorry. No, changes for the future. Changes are never done. All right. Why can the top alkylation product, the one with the newly added allylic group, Why is it that this cannot go through hydrolysis and decarboxylation? How come this one can't go through hydrolysis and decarboxylation? Trick question. Yeah. Good job, Elena. Same, yeah. Actually, you bring up a good point, James, which is that alkenes, we know, react in acid, especially aqueous acid, to go through acid catalyzed hydration. So we might run into some side reactions. Might not be the most desirable thing for us to do. But in theory, absolutely, I can hydrolyze the esters and decarboxylate one of them, for sure.
And that would look the exact same as that product, just the group on the bottom be different.
Exactly. This carbon chain would include the alkene instead. If you guys look ahead at the practice final, I love to have these in my roadmap because they're fun. And then I can do intramolecular stuff with them afterwards, you know? Like hydroboration oxidation of that alkene to create an alcohol, and then esterification within the ring for that alcohol. Yeah.
I was going to tell you that the final, only the key is out right now.
Oh,
The blank version.
I'm glad you brought that up.
At least on my end.
Thanks for mentioning that. It's kind of not useful in the way that I want it to be. I'd rather you not have the key than anything, you know? I think it's better to be able to test yourself than just see the correct answers. Yeah, sure enough. Just straight up didn't add it. All right. Questions on alpha carbon substitution before we move on?
So the beta acid, whatever, when it's two carboxylic acids stuck together,
Mm-hmm.
that won't react with itself without the heat. That is just like a stable intermediate-ish.
I mean, I wouldn't call it an intermediate necessarily, unless you take it further. It is a stable structure, absolutely.
Okay.
There are many beta acid acids out there, beta dicarboxylic acids. They're stable on their own. It requires getting into that transition state where the carboxylic acid of one group is lined up well with the carbonyl of the other group. That's just part of it, though. The electron movement is a whole other part. That also takes energy. So being in that conformation with the right energy to make and break all of those bonds, that's what takes the heat.
Okay.
And yeah, just like an heat. Sorry, go ahead.
So if you just like added aqueous acid, you could just stop there and get the, I keep forgetting what you call it. What,
The hydrolysis product.
yeah,
Absolutely.
okay.
You could just add acid and stop there. In fact, maybe I'll try to show you guys this problem on active that is not set up well. One of your classmates emailed me about it because it's confusing the way that it's written, and I can clarify my expectations for it and how you can navigate it. And I guess I'll clarify my expectations of how I'll show it. You guys finished chapter 22 already on active? Okay. When is it due? It's got to be soon, right? Tomorrow? Oh, this is not the same problem. I'm in the wrong chapter, aren't I? Yes, I am. Oh, you can't see anything. That's fine. That's fine. You didn't need to see that. H3O plus and heat. Well, that's exactly how I show it to you. Hydrolysis and decarboxylation. Easy. Then it says H2O heat minus CO2. I already lost the CO2, didn't I? I want you guys to read H3O plus and heat and instinctively see that it decarboxylates, forms an enol, and tautomerizes back to the carbonyl. So all I do is cleave off one of my carbonyls, the carbonyl that can become an acid. So why is it that it's saying H3O plus and heat, and then in the next step it's saying lose the carboxylic acid? It's not set up well. If I could have modified this, I would have said H3O plus alone. It is true that you're probably going to have to heat this a little bit because hydrolysis takes energy, and to make that happen, it'll be warm at least. Then I would have said heat, and in parentheses, lose carbon dioxide, minus CO2. That's what it's trying to indicate. So much like how I'm showing you here, ester to acid to decarboxylated product. That's what they're expecting. Show me hydrolysis, then show me decarboxylation. Exactly. The intermediate they're asking for is what I've got in brackets, more or less.
So that before it's tautomerized?
Mm-hmm.
Okay. It wants us to show both of those steps.
Correct.
Okay.
But unfortunately, they're listing it as the reagents that I give to you as all of it at once. So it's confusing. This is question 11 on chapter 22. It's confusing because your instinct here should be assume hydrolysis has happened, assume decarboxylation has happened, show the final carbonyl product. But then what else is there for you to do? And they want you to show the hydrolysis, then show decarboxylation, because those are really the two steps happening here: hydrolysis and then decarboxylation. Okay. You guys want a break then? Okay, in that break, I am going to re-upload what I have here under the worksheets because I have combined them a little bit. So for the worksheet I just handed out is uploaded differently on here, and I'm going to combine those. Yeah, take a 5-7 minute break. Let's come back at the top of the hour. I guess I should have done this very different. Oh no, see, there's something missing.
I had a question.
Yes.
So on the last written work, there were two possibilities, and I did one of them.
Yes.
But the other one, I actually spent a lot of time trying to think how to do it, but I couldn't do it.
Okay, let's talk about it.
So I guess my main point of confusion is the fact that basically we need to reduce the amide side, but we also need to oxidize the aldehyde so that these and these react. That was my idea.
Good.
But if I do one, like say, if I try to reduce this, then I reduce this. But if I try to oxidize this and I realize, I think permanganate would react with this as well.
What would it do with the amine?
Doesn't it also turn it into, I thought it would reduce it into like and also, I guess in the presence of water it would, but I thought it would turn it also into like a, not a carboxyl. Oh. Maybe I got confused with acetonitrile.
Well, actually, so potassium permanganate as an oxidizing reagent is not likely to oxidize the amine.
Okay.
It's also not likely to oxidize the nitrile.
Okay.
And that's because the nitrile is already very oxidized.
Yeah.
It's got 3 bonds to nitrogen. You can't replace it with anything else. It's already oxidized.
Okay.
You can reduce the nitrile. You can add hydrogens to it. In terms of the amine carbon, maybe the amine carbon gets oxidized. We've talked about how benzylic positions can be oxidized into carboxylic acids, but the presence of the amine is going to change that.
Okay.
And the nitrogen itself, the only way that it gets oxidized is if it leaves as like hydrazine
Okay.
or elemental nitrogen into.
I mean, that would be pretty difficult without benzene, right?
So here's something that we can try to do to figure out if anything might happen. Let's search. I don't like AI overviews
Okay.
because a lot of times they just tell me what they think I want to hear and they don't necessarily know what I want to hear. But let's see if a benzylic amine with oxidizer gives us anything of interest. All right, well here we've got benzylic hydrocarbons that we already knew about. This is also benzylic hydrocarbons. This is actually the exact thing we're talking about,
Okay.
but it's giving these reagents that aren't specific, right?
Are you guys lab partners?
This, again, like, this has got other reagents necessary, so I can't say with certainty
Okay.
Chris, is your lab instructor?
that the nitrogen there is going to do anything.
Okay.
In fact, I think the nitrogen there is going to inhibit anything from happening.
Oh, okay. It's like an inhibitor.
So your synthesis is exactly what I was looking for.
Oh, okay. So this was correct.
Yep,
Okay.
perfect.
I wasn't sure if this was gonna mess it up. That's why I was wondering. It's like, yeah.
So this one was full reduction followed by partial oxidation.
Yes.
And the other one was full oxidation
Yeah.
followed by selective reduction. That was my goal.
Okay.
Utilize oxidation and reduction in different ways to get that final product.
Oh, okay. Awesome.
Good work.
Well, thank you.
You're welcome.
You're like, I can tolerate people, but there's just some people that you're like, yeah.
he's my pharmacy advisor. Like, yeah.
What'd you tell him?
I was like, well, I have to take biology there.
And physics.
Really, that's the only reason? And I was like, well, I honestly don't think I could pass your class. And he's like, well, there's people that were in your, that was your professor that are passing my class, and it's like these 3 girls that are in high school that don't have a job.
Yeah.
Yeah.
High schoolers taking OChem too?
You actually make
Yeah, it's crazy. I don't actually, it's amazing actually.
I didn't know that was even possible.
I didn't either. It's through like New England.
Oh, actually, that's not true. I taught a high school student OChem 1 once. He was here on like summer vacation.
Oh, okay.
Yeah, he went to a school in Oklahoma, and his brother lived in Salt Lake City, but he's from California, so he moved to Salt Lake City for the summer and took OChem with me here at Slick. And then he came in to take the final early because he was leaving. And he said, yeah, I just turned 17. I graduated high school a year early, and I am like on track to be a pharmacist or something. And I was like, okay, well, don't forget that you are so young that by the time you become a pharmacist, you might have found other passions in life. So leave the door open. Don't tell yourself at 16 that you're going to be a pharmacist just because you can become a pharmacist at 22. Like, that's crazy young. All right. Well, enough of that substitution stuff. Let's get back to the fun types of reactions like addition and elimination. The next class of our reactions are called addition and condensation reactions. Oh, I remember a functional group I forgot to tell you last week. Yeah. Yeah, the Aldol. Okay, well, if you have the ability to squeeze this one back into your notes, let me remind you some of the functional groups I told you about. You guys remember these? Conjugated carbonyl, alpha beta unsaturated. Beta carbonyl, like what we just talked about with acetoacetate or malonic ester or the decarboxylation. This one, yeah, shared beta, dicarbonyl. The functional group I forgot to give you was this one. I'm very upset at myself. How could I miss that? What would you call it? You'd call it an Aldol, really. Like if you just came up with it. Or if you followed the pattern that I've been kind of establishing. Did you notice there's no alcohol, or there's no aldehyde in here? So like ald.
Yeah, beta alcohol, carbonyl.
Good. And since carbonyls outrank alcohols, we will refer to the alcohol as its substituent name. So instead of beta alcohol carbonyl, we'll call it not oxy. Oxo is what a ketone or aldehyde is. Lily? Oh, I thought you were saying it. Yeah, beta hydroxy. You called it droxy?
Oh, I said oxy and, oh, I forgot hide.
Right. Hydro. You forgot the, yeah, okay, hydra. Hydro. Right, okay. Now, the first class of addition and condensation reactions that we're going to look at are called aldol addition and aldol condensation. And this name is not a dead guy's name, which honestly, like I wouldn't be surprised if someone in Germany in the 1800s was named Aldol. Seems reasonable. Adol. But it is a composite that is meant to tell you what functionality is there. And that is, it's referencing the aldehyde and it's referencing the alcohol. And that's because together on the same molecule, you can have an aldol alcohol. To be better, I'm actually gonna, I'll use this idea of the aldol alcohol, aldehyde alcohol, the aldol, as a way of showing how we get to that. The problem is ketones work just as well here. So the aldol is also perfectly happy being a ketol. So I want you to remember aldol refers to reactions with aldehydes and ketones. It does not refer to reactions with esters. That's the gist of it. Addition is pretty simple. We will add across a carbonyl. We'll do acyl addition. Condensation refers to the idea that one of the byproducts will be a small molecule. We will condense out of the reaction a small molecule, usually water or an alcohol. So let's demonstrate. I've got this molecule for you. I named this earlier. I wonder if you guys remember what its name is. There's a systematic name and then there's a common name. Yeah, that guy right there. An acidic aldehyde. What do you mean by acidic? Well, we know the alpha hydrogen is surprisingly acidic. It's because it's in resonance with the carbonyl. But in general, like, it's not any more acidic than any other aldehyde. In fact, because of its substitution, that alpha carbon is less acidic than other aldehydes. But could you name it? Its name definitely isn't acidic aldehyde, right? Acetaldehyde. It's a 2-carbon carbonyl compound. And that means that it can get the ACET prefix, acet. It's not acetic acid, it's not acetate ester, it's not acetone, it's not acetamide, it's not acetyl chloride, it's acetaldehyde. That is what? Its systematic or its common name? Common name. So what is its systematic name? Ethanal. Does that name ethanal make sense?
Yeah.
2 carbons. No alkene, no alkyne functionality, so it gets the root ane, and then we stopper ane with al. Okay, so I am buying time. I have 3 reactions coming from it. but I don't know what the third reaction is that I meant to show you. So I'm trying to. Yeah, I'm looking back at last fall's. That's a nice outfit. I forgot I wore that outfit. Sorry.
This 2 times, what does that mean?
Yeah, well, it means we're going to assume 2 equivalences of that aldehyde.
Oh, that's.
And I know there are people in this room that understand it better when it's very clearly written how many equivalences are there. Yes, I was talking about you. So yeah, we're talking about having 2 equivalences of the aldehyde, which is to say, this just happens when you have it, right? And so these reactions, we've talked about reactions earlier that will actually utilize some of the same reagents, which means that these reactions can compete with each other. I'm not seeing it, is the problem. I'm not sure if it's just I'm not in the right spot or what. Yeah, I don't love making them up. Oh, I do. Okay. It's because it's one that I'm not going to use very much. Except now I have to remember which way it goes. So we're gonna be running acidic conditions and basic conditions once again. The acidic conditions, I think, are kind of is a runaway reaction, and because of that, we don't always use acidic conditions. If I have 2 equivalences, my 2 equivalences can react together with acid, and it gives this product. What kind of functional group is that? It was one I had just previously listed on the board. A what? An allylic aldehyde. Well, actually, we might call it a vinylic aldehyde, since the aldehyde carbon is directly connected, but not the term that I had given you guys previously. A conjugated carbonyl, a conjugated aldehyde. There is a non-stop sequence of p orbitals, so that entire 4-atom sequence is conjugated. And then the other term that we could use to describe a conjugated carbonyl, this is an alpha-beta unsaturated carbonyl. All right, well, here's the beauty of this. I'm going to draw out my second equivalence. If this is alpha, mapped into my final product, then where is beta? The carbonyl carbon of the second equivalence. This is a condensation reaction. That means a small molecule has been condensed out during this process. What byproduct do I form? Water. So it should be obvious where the oxygen for the water came from. That beta carbon was a carbonyl carbon, and it no longer has an oxygen. So one of the aldehydes has given up its oxygen. Where do the hydrogens come from, though? That's a lot of hydrogens to lose. Where did I lose them from? The CH3, this labeled alpha carbon, was CH3, but now is CH. So I have condensed water out of this using acid. Is acid being consumed in this process? Is it a reagent, or is acid a catalyst? It's a catalyst. I've got equal parts in my product from my starting material. I'm just using acid to catalyze this reaction. There is an intermediate that is stable in basic conditions, but is not cannot be isolated in acidic conditions. So, in basic conditions, let's say I run NaOH. I can control how far this reaction runs. Once again, I can get the alpha-beta condensation product, or, to get there, I usually need excess NaOH, or I need heat. I'm going to be straightforward with you guys and say that requiring excess or heat is not something that I will take points off on an exam for or a unit test. In fact, I try to be quite clear whether I'm going for this product or the other one that it can do. So acid can give the conjugated carbonyl, base can give the conjugated carbonyl, but base can also give this intermediate. It can stop at this intermediate. What functional group is that? I erase it. Yeah, but I don't like the name Aldol because they use Aldol for the condensation too. And I get that this is the intermediate on the way to the condensation product, but I don't like it. Good. Beta hydroxycarbonyl. The aldol. The aldehyde alcohol.
Do we always form the trans double bond?
Good question. Why is my alkene trans instead of cis? It does have the capacity to do either, so it generally will form whichever one is the lowest energy to form, and that generally is trans over cis. But stereoisomerism happens, so you may get a cis alkene as a minor product. All right.
And the difference between those two is, on the top one you're using excess.
Correct. Correct, which is such a small difference, right? And so generally I will ask for, show me either the condensation product or, I will say either show me the condensation product or show me the addition product. So to the right, we're looking at aldol addition. Above and to the left, we're looking at aldol condensation. And like I mentioned earlier, the addition product is formed on the way to the condensation product. It's kind of like how the hemiacetal is formed on the way to the acetal. Very much the same.
So you say it's like an intermediate?
It's an intermediate, absolutely. It's an intermediate in both acidic condensation and acid catalyzed condensation and base catalyzed condensation. But in acid catalyzed condensation, it is too reactive to the acid catalyst, and so the addition intermediate can't be isolated. It will just keep reacting. In base catalyzed conditions, you can control the conditions well enough to isolate the addition product. Next week, you guys are doing chalcone synthesis in lab, and you'll be doing a aldol condensation reaction. And the funny thing is you won't actually add heat or that much excess base. So to limit the control, I think would require very cold temperatures. Run it in an ice bath type reaction. Okay, true or false? These reactions cannot be done with ketones. False. So let's do some practice problems with some ketones. Well, we worked with acetaldehyde, so why don't we show the addition product and the condensation product with acetone. If you know what functional group to form, you can just start by drawing that functional group. Then you can start mapping where alpha and beta have come from in that functional group and map them into your starting materials so you know how your carbon chains should look. Notice on the top reaction there I've said, give me the addition product, because again, with NaOH, it can be hard to clarify whether you're stopping at the addition intermediate or going all the way to the condensation product. Also, have you noticed how when I gave you the beta hydroxycarbonyl, I drew the carbon chain a certain way? And now that I'm giving you a beta hydroxycarbonyl, my carbon chain is drawn a different way. That's on the wrong position anyways. All of that to say there's no, oh, that was correct. There's no one conformation for these functional groups. They are wiggly little guys, and they rotate as such. So as long as you are mapping your carbons correctly, look at alpha, look at beta. Actually, I didn't do that here. Alpha, beta. You can map your acyl addition and your carbon chains by mapping alpha and beta to the two equivalences. Sorry. Close. You're missing a carbon here, and you're missing a conjugation and a carbon here. You notice this is just a ketone, right?
Yeah.
Not a conjugated ketone.
Yeah.
So it might help, instead of copying my 2x, it might help to actually copy two equivalences and label on one of them the alpha position and then map that to the products. Label on the other the beta position and map that to the products.
This is a dumb question.
No, this is great.
This can be alpha as much as that can be alpha, right?
Correct. Correct. It wouldn't matter which one, but Lily, beta was not an alpha carbon. Yeah? Where did beta come from? Beta was a carbonyl carbon. Carbonyls are electrophiles. So for a carbonyl carbon to become a beta carbon, alpha would have to attack beta. Carbonyls are good at doing that. They're good at being attacked. carbonyl carbons become betas by being attacked by alphas. I sound like just start a podcast.
With the two equivalences, would they be connected?
In the final product, yeah.
Okay, so
Yep.
that's how we can see like this guy, if they're connected, that would be the alpha and that would be the beta. That's how I can see that.
Sure, yeah.
Okay.
Now, here's alpha. Alpha has attacked beta. Here's beta. Beta has methyl and methyl.
Oh, two methyls.
I apologize. Sorry, let me take a step back. Here's alpha. Alpha attacks beta. Here's beta. Beta has methyl and methyl. Beta has methyl and. Good.
But the double bond, that is.
Yep, because this is the condensation product.
Okay.
Now let's do the same thing here. Here's alpha. Well, first of all,
You say alpha attacks beta?
correct. We'll look at the mechanism. Beta has two methyls.
With that, can I just add that like?
Perfect. Exactly that. It is weird. Great. Oh no, sorry. You added it to the wrong spot.
Damn it, I went back and forth on that one.
Yeah, those are right.
Where is it this one?
So here's beta.
Yeah,
Oh no, that's an alpha carbon.
no, that's the alpha. This
Yeah,
is the
that's
one
alpha.
we did.
Alpha attacks beta.
Right there.
Beta is a carbonyl carbon. Beta is not an alpha carbon. Okay, so here's carbonyl, which does not have a name, right? We just call it carbonyl carbon. The first carbon off is alpha,
I get it now.
then beta. Where did this beta come from in the final product? It was a carbonyl carbon. In fact, I'm going to write it down so that that is something you write down. Beta was a carbonyl carbon. This is OChem lore. Like, I think this could be the secret code into the OChem club. Beta was a carbonyl carbon.
Is that one?
Close.
That one?
It's very close. Here's alpha. Here's beta. Alpha has carbonyl methyl. Beta has methyl.
Wait, what?
Yeah, alpha has carbonyl methyl.
Oh.
Beta has methyl.
But I thought that it turned into an alcohol with the NA.
Yep, you're right. The addition product is an alcohol, but you don't have enough carbons connected to beta.
Oh, so it has one more carbon.
It does have one more carbon.
Like that?
Great. Any direction would be fine. But what we're recognizing is that alpha bonds to beta. Acyl addition leaves me with an alcohol.
Oh, and then the beta has two.
Beta already had two methyl groups.
And then oh, okay, that makes sense. Thank you.
Good.
Now.
Yep, you did. You got it. Great. You already had it. Good. Beta was a carbonyl carbon. Good. Very close. But remember that beta carbon has two methyls coming off?
Right.
That's the beta carbon.
Oh, right, okay.
In addition to the alcohol, it still needs to have two methyl groups.
Okay, so,
We're running acyl addition, so my carbonyl becomes an alcohol.
I'm not sure what I'm doing.
I see it. I see. Are you trying this one? Are you trying this at the bottom?
Yeah.
Where are you trying? Here?
Here, yeah.
This is very close,
Okay.
but you've combined alpha and beta rather than having the connection between them.
Okay.
Once we look at the mechanism, it might make more sense.
oh,
Yes.
Okay.
Yes.
Okay, I was thinking if I did that,
That was exactly it. Okay. Sodium hydroxide, I'm looking for the addition reaction. All right, I'm going to space them out again. I'm going to say that this alpha runs nucleophilic addition, acyl addition onto this carbon. When alpha attacks this carbon, it will become the next carbon in sequence. It will become a beta carbon. Some tricks on how to draw these now that you've already kind of wrestled through it. I'm going to draw my two equivalences next to each other. Get rid of my carbonyl because that's actually going to be attacked. And acyl addition that carbonyl. Now I have my chain. Or draw the two equivalences side by side. And again, have alpha reach over and attack this carbonyl carbon and open it into an alcohol. It's messy. It is. There's no perfect way to do it. But again, I think the best way is recognizing that when alpha attacks beta, you get this new bridge between them. By the way, this was the answer that we were looking for. This is the, I know. This is the acetone aldol addition product. Okay, the condensation product is actually pretty easy. Now I'm just going to remove a second alpha hydrogen and the hydroxyl group from beta. Or again, what I can do is kind of set my equivalences next to each other and then bridge the alpha carbon to be double bonded to the beta carbon. Now that one actually fits in a lot more nicely because I really just have to erase the O and then connect. That's where alpha is going to be. But this has different conformations that it can be shown in as well. It can rotate around. So this is just as valid. Again, just recognizing that alpha has attacked beta. Cool. Let's talk about some complications that we get into. It's not all the time that I want to react the same exact reagents with each other and create condensation products or addition products from just one starting material. Although actually, calling back to the complications that from earlier reactions, if I'm, say, trying to halogenate at an alpha position, and I've got base in here and chlorine, well, it turns out my base can accidentally run addition between my two components. So if I'm trying to do that alpha substitution, I might run into accidental byproducts of aldol addition. Same thing with acid. If I'm trying to use acidic conditions, I might accidentally run aldol condensation when I'm trying to do alpha carbon substitution. Okay, so on this next flow chart, we've got acetone and acetaldehyde. And we're saying that there are 4 different products that can form. Why? And for clarity, let's look at the 4 condensation products that can form. We're not looking at addition products here. Okay, where is my alpha and where is my beta? We already know that acetaldehyde's alpha position can be alpha And if I have both of these present, that means that another equivalence of aldehyde could also be beta. I might have the alpha of acetaldehyde attack the carbonyl of another acetaldehyde. But my beta carbon could have also come from acetone. So I have these two competing products that form from the acetaldehyde as the nucleophile. But nothing is stopping acetone's alpha carbon from being the nucleophile. And we already know that acetone can attack another equivalence of itself, or acetone could attack the acetaldehyde's carbonyl carbon. The name that we give to this is crossed aldol condensation, or crossed aldol addition, but in all honesty, I lean into the condensation a little bit more because there are reactions that we can use with the condensation products. There's not a lot of reactions that we use with the aldol addition product. I do want you guys to look at your molecules that you're analyzing this semester, because there are several, especially biologically active molecules that have these beta hydroxy carbonyl structures that can be formed by aldol addition. So if you're thinking about synthesis for your compound and you've got a beta hydroxy carbonyl, you could run aldol addition. Okay, once again, we call this crossed aldol. Can you understand why we call it crossed? It's mixing different reagents, and we need to overcome it. So let's get rid of these multiple products. I would like you guys to devise a compound that can react with cyclohexanone one that limits crossed aldol reactivity by limiting alpha hydrogen placements. If you can each try to think of something that will limit alpha hydrogen, which means I limit positions that can even be the alpha nucleophile. And then whoever has the best one will run with it on the board. Maybe give me some ideas. You don't necessarily have to jot it down, but how could I limit alpha hydrogen possibilities? Does cyclohexanone have alpha hydrogens? Definitely.
Yes.
Yes. So what could I react it with that would limit my alpha hydrogens to just being on cyclohexanone? Let me phrase this again. In my crossed aldol, both the aldehyde that I introduced and the ketone that I introduced, the two carbonyls I introduced, both had alpha hydrogens. They both had a potential for becoming the nucleophilic carbon. If I can limit alpha hydrogens, I can limit the nucleophilic carbon. I want this to be the only nucleophilic carbon, suggest a compound that would not have alpha hydrogens? Oh, I thought he was raising his hand. And make sure it's an aldehyde or a ketone, otherwise it's not aldol. Ditert-butyl ketone? Well, of course, why did I say it like that? Like there was any other option. No alpha hydrogens on it. By the way, you don't have to write that as TBU. You can draw out the 3 methyl groups so that you can feel confident there's no alpha hydrogens. But now there is only one possible alpha position. Do you guys want to see the addition product, or do you want to see the elimination or the condensation product? Both? We weren't quite effective enough. First of all, I did not give you all 8 products. Maybe you guys recognize that we could have had the aldol addition at each of these places where we only showed the aldol condensation. So we technically had a combination of 8 possible products with our cross-aldol reaction. And now I'm saying we've narrowed it down, we've cut it in half, but there actually is still some competitive behavior. What else could possibly form? What are we missing? One more time. Dimerization. Cyclohexanone reacting with cyclohexanone. We know that ditert-butyl ketone cannot do aldol addition or condensation on its own. It has no nucleophilic alpha carbon. It has no alpha hydrogens to turn into a nucleophile. But cyclohexanone can still do acyl aldol addition on itself, and it can still do aldol condensation on itself. So we have to be mindful of that. I have limited the number of places that I can have an alpha carbon, but that doesn't mean that I can't have self-competition. Especially given that tert-butyl on both sides of a carbonyl is very sterically strained. Cyclohexanone has less steric strain, so it may be easier for the bottom reaction to run. So how do we continue deriving these reactions with better and better efficiency? Our next step is to promote selective reactivity. Whatever that means. Well, let's go beyond making both of them the same carbonyl. Let's make one carbonyl even more reactive. So this one I gave us 2-butanone. What could I react 2-butanone with where the missing reagent is always a better electrophile? Where the missing reagent, still does not have alpha hydrogens available to it, but also is more readily attacked than 2-butanone itself. What is a better electrophile than a ketone? And falls within our realm. Aldehydes. But not a lot of aldehydes don't have alpha hydrogens. I could do benzaldehyde. Benzaldehyde has no alpha hydrogens because the one side is benzene. I could do butylaldehyde, or I could do formaldehyde. And if I did formaldehyde, it is a much better electrophile. It has very little steric strain. It has very little induction. I'm going to show this two different ways, though. I'm going to give you this aldol addition and this aldol condensation. But I also want you to consider this aldol addition and this aldol condensation. The products I'm showing to you are structural isomers. They're nothing different than different alpha hydrogens reacting. How do I know which of them is going to form? Also, I apologize. I've been meaning to be a little bit more proactive about labeling my alpha and beta positions. Obviously, these reactions must be done in basic conditions, because if I'm able to even predict an aldol addition product, I must be looking at basic conditions. There must be a difference between the bases I use in these conditions. Would you agree? What base could I utilize in each of these cases? What's the difference between them?
Should be the sodium hydroxide with the heat.
For which one? To get this red product combination or to get this black product combination? How would I be able to control my ketone attacking from its more substituted alpha carbon versus controlling my ketone attacking from its less substituted alpha carbon? How do I guide that regioselectivity? A bulkier base. A thermodynamic base for the more stable, more substituted position. A bulkier base for the less substituted but less stable position. Great. That's exactly it. The size of my base can play a role in whether I go to one side of a ketone or the other. Okay, lastly, this crossed aldol example that I gave you guys before already utilized one of the controls that we've mentioned, which means not all of these are likely to form just as well as each other. What control did we already contribute that we just didn't consider? Did we limit alpha hydrogens between the two reagents? No. They both had alpha hydrogens. So did we promote selective reactivity? We did. We had a ketone which is less electrophilic than an aldehyde. So we are more likely to have products where the aldehyde was attacked. When the aldehyde is attacked, these products. Did I not do a good job of labeling this? Here, when we attack the aldehyde and when the aldehyde attacks itself, those products are more likely to form because that is selective reactivity. The aldehyde is more reactive than the ketone. Andy, you were staring down here at these. Do you see how terp butoxide will only go to the most accessible hydrogen? It's big and bulky, so it doesn't want to fight against all the rest of this steric strain. It goes for wherever is the most accessible. Okay, we'll talk about principle 3 on Thursday.
Could NaOH go to either of those spots?
NaOH has a preference for the most stable base,
Okay.
the most stable enolate.
Okay.
Okay. Complete enolization as a method for forming exactly the product you want coming up. Have a good night. See you guys Thursday.